Okay, the precise definition of a limit. So let's look and see what this is. Let f of x be defined for all x's that does not equal a over an open interval containing a. Let L be a real number. Okay, so we're going to look at a function that's defined for all x's except for a. X does not equal a over an open interval containing a. So, and L is a real number. Then we have what we've been talking about. The limit of a function as x approaches a equals L. If for every epsilon greater than 0, there exists a delta greater than 0. Now, these are just Greek letters, epsilon and delta. Such that if, and so here we have an inequality, if the absolute value of x minus a is greater than 0 but less than delta, so it can't be 0 or less than 0. It's got to be a small number, but it's going to be greater than 0 but less than delta. All right, then we have f of x minus L, the absolute value of that quantity, less than epsilon. So again, all of this comes from our limit. Here's my x minus a. So as we're getting closer and closer to to a, right? As x minus a, that's number is between 0 and whatever delta is. And then we're looking at our function, f of x minus L, is less than epsilon, and it's the absolute value of these. So let's look at this a little more. Okay, so let's see what this, if we can translate it to make it understandable. For every epsilon greater than 0. So for every positive distance epsilon from L. Okay, so for every, it's got to be positive, greater than 0. Positive distance epsilon from L. There exists a delta greater than 0. So that's, again, a positive distance of delta from A. Such that, well, that's what that means. Such that if we look at this x as x is closer than delta to A, and x cannot equal A, then f of x is closer than epsilon to L. Okay, so this is going to be really, really close, closer than epsilon because it's a number greater than 0. And then we're looking at this distance being closer. Okay, so x is closer to delta than delta to A. So recall that the distance between 2 points, A and B, on a number line is given by the absolute value of A minus B. So that's what we're looking at when we're looking at our f of x minus L and our x minus A. So look at what, here's just some examples of what these mean, and hopefully will help with that epsilon, our precise definition. So 10 minus 6, the absolute value of that equals 4. That's the distance between 10 and 6. It's 4 units. Okay, 6 minus 10, well, the absolute value of that is going to be 4. So again, the distance between 6 and 10 on the number line is 4. Negative 6 minus 10, that's negative 16. Absolute value of that is 16. So again, that's the distance between negative 6 and 10. If you look at your number line, you can see how far, what's the distance between these two values on the number line. And x minus 10, now we're throwing a variable in there, equals 5. So this means numbers whose distance from 10 is 5 units. So we don't know what x is. We know it's a number, but that number's distance from 10 is 5 units. So we can figure that out. What about the absolute value of x minus 10 less than or equal to 5? What does that mean? Means numbers whose distance from 10 is less than or equal to 5. So it's an interval. It's less than or equal to 5. And then absolute value of x minus 10 greater than or equal to 5 means numbers whose distance from 10 is greater than or equal to 5 units. So let's look at what we have. All right. So for that first one, we have x minus 10 equals negative 5, or x minus 10 equals 5. So you might remember what it's, how do you solve an absolute value equation? You split it into two equations, and that's what we did for this first one, if it's an equation. And then we can solve this and find out what x is. Okay. What if it's an inequality? All right. Well, if it's a less than, then we write it as a two-part inequality. So we have x minus 10 greater than or equal to negative 5, x minus 10 less than or equal to 5. Then if it's a greater than, we split it into two inequalities. And you can see we reverse the symbol, or the inequality symbol, but when we have negative 5, similar to what we did up here, except that's an equal sign, this is an inequality. So we switch it for the negative, and then we have x minus 10 greater than or equal to 5. So let's look at our statement here. And what it is, the statement, the absolute value f of x minus L is less than epsilon. That means the distance between the fx values and the value of L is less than the value of epsilon. So it's going to be really, really close. It's less than epsilon, and if epsilon's a small number, then our f of x minus L, or the absolute value of that's going to be very small. So look how we can rewrite this. Remember, this is an absolute value, and we can do the same thing. We will have f of x minus L is greater than a negative epsilon and less than epsilon. And then we can solve that by adding L to both sides. So there's our function. Our function is greater than or equal to L minus epsilon and less than or equal to L plus epsilon. So that's a distance. Remember what L is. That's the limit of our function as it approaches whatever value we're approaching. Okay, and the statement. So here we have the absolute value of x minus a is greater than 0 and less than delta. That means the distance between the x values and the value of a is less than the value of delta, and the value of x is never the same as the value of a. Remember, that was in our definition. Or, again, we split this into a two-part inequality that we're looking at. We have x minus a is greater than negative delta, and x minus a is less than delta. And if we solve that for x, you can see what we have here. And remember, x cannot equal a. So that's part of our definition, precise definition. Okay. So let's go back and look at our limit of f of x as x approaches a equals L. If for every epsilon greater than 0, there's a delta greater than 0, such that the quantity f of x, or the absolute value of f of x minus L, is less than epsilon whenever the absolute value of x minus a is greater than 0 or less than delta, or you can think of it as between 0 and delta. That distance between x and a is between 0 and delta. Or, and again, we can look at our function value and just think about, and we'll look at some pictures of this, or some visual representations of these, and that might help as well. So the function value f of x is greater than L minus e and less than L plus e whenever a minus delta, or x, is greater than a minus delta, less than a plus delta. X cannot equal a. So an example, write the appropriate Epsilon-Delta definition of this limit. Okay, so let's look at it. For every epsilon greater than 0, there exists a delta greater than 0, such that, so there's my x minus a, that comes from right here, absolute value of that, and that's going to be between 0 and delta. Then we have x squared, there's my function f of x right here, minus 9, the absolute value of that is less than epsilon. Let's look at another example. Write the appropriate Epsilon-Delta definition. So we're just writing the definition. For every epsilon greater than 0, there exists a delta greater than 0. Now, hopefully you see a little pattern here, such that if the absolute value of x plus 1, remember what our precise definition was, it'd be x minus -1, x plus 1 is between 0 and delta, then the absolute value of x cubed minus 3 minus -4, that's L, f of x minus L, is less than epsilon. Okay. Proving. Now, this isn't a proof class, but I think it's important that you see some of this. It's not something we're going to focus a lot in this particular calculus class, but I think it's good for you to be aware of it. How do we prove that the limit of 2 of x plus 1 as x approaches 1 equals 3? Well, let's look at that. All right, so if we look at our precise definition, for every epsilon greater than 0, there is a delta greater than 0, such that the absolute value of x minus 1 is between 0 and delta. Then our function, which is 2x plus 1 minus L, right, minus 3, is less than epsilon, the absolute value of that quantity. So let's prove this. All right, so there's our, let epsilon be greater than 0. We need to choose a delta. Okay, we're going to choose a delta. We need to find this number, so we're going to find it. So here's what we have. Remember, f of x minus L is going to be less than epsilon. And I can simplify what's inside, right? That's going to be 2x. Absolute value of 2x minus 2 is less than epsilon. I can factor that 2 out. So you can see we factored the 2 out, less than epsilon. And then divide by 2. We're going to get that absolute value by itself. And compared to the given, we have x minus 1, the absolute value of that is between 0 and delta. We see that delta equals epsilon over 2. Works. In fact, any delta less than or equal to epsilon over 2 will also work. So we found the largest value that will work. Now we can fill in epsilon over 2 for delta above. So we're going to plug that in for our delta. So there's our delta right here. You can see our epsilon over delta. Or we can say that's what our delta equals, excuse me. So given the absolute value of x minus 4 is between 0 and epsilon over 2, we have that we know that our function f of x minus L, the absolute value of that, is less than epsilon.